The information in this video comes from thorough research. Please share your thoughts on the video, The Birth of Quantum Physics, in the comments. We'd love to hear what you think. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Niels Bohr. The Quantum World, a journey through the foundations of reality. The birth of quantum physics. The classical era and its limitations. At the end of the 19th century, physics appeared to be a nearly completed science. Newtonian mechanics, thermodynamics, and Maxwell's electromagnetism seemed to explain all known physical phenomena. Many physicists believed that the universe operated like a precise machine, predictable and deterministic. However, cracks began to appear. Some experimental results did not match predictions from classical theories. Among these, the most significant anomalies involved blackbody radiation, the photoelectric effect, and atomic spectra. These discrepancies set the stage for a revolutionary transformation. Max Planck and the quantum hypothesis. In 1900, German physicist Max Planck proposed a radical idea to solve the blackbody radiation problem. Classical physics predicted that an ideal blackbody should emit infinite energy at short wavelengths, a contradiction known as the ultraviolet catastrophe. To fix this, Planck suggested that energy is not emitted continuously, but in discrete packets called quanta. He introduced the constant h, now known as Planck's constant, which relates energy, E, to frequency, F, through the formula, E equals h asterisk F. This idea, meant initially as a mathematical fix, became the foundation of quantum theory. Einstein and the photoelectric effect. In 1905, Albert Einstein extended Planck's idea by proposing that light itself is made of quanta, later called photons. He explained the photoelectric effect, where light shining on metal releases electrons. Classical wave theory couldn't explain why only certain frequencies caused emission, but Einstein's quantum theory did. His work earned him the Nobel Prize in Physics in 1921 and confirmed that light behaves both like a wave and a particle, a core concept of quantum mechanics. Bohr's atom and quantized orbits. In 1913, Niels Bohr applied quantum ideas to atomic structure. He proposed that electrons orbit the nucleus in fixed energy levels and can jump between these levels by absorbing or emitting photons. This model explained hydrogen's spectral lines and marked a major step in developing quantum theory, though it couldn't fully explain more complex atoms. The principles of quantum mechanics. Wave-particle duality. One of quantum mechanics' most puzzling features is wave-particle duality. Particles like electrons can act both like discrete particles and continuous waves. This was first confirmed in the double-slit experiment, where single electrons sent through two slits create an interference pattern, a result characteristic of waves. Heisenberg's uncertainty principle. In 1927, Werner Heisenberg formulated the uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be known precisely at the same time. The more accurately we know one, the less accurately we can know the other. This principle challenges classical notions of determinism and places fundamental limits on measurement. Schrödinger's wave equation. Erwin Schrödinger introduced a mathematical description of quantum systems through his wave equation. The solution to this equation, the wave function psi, contains all the information about a quantum system. The square of the wave function's magnitude, psi superscript 2, gives the probability of finding a particle in a given location. This probabilistic nature is at the heart of quantum physics. The role of measurement. In quantum mechanics, measurement is not passive. It actively affects the system. When a quantum system is observed, its wave function collapses to a definite state. Before measurement, a particle can exist in a superposition, being in multiple states simultaneously. This idea led to deep philosophical questions about reality and observation. Famous quantum paradoxes. Schrödinger's cat. Erwin Schrödinger illustrated the strangeness of quantum superposition using a thought experiment. A cat in a sealed box with a radioactive atom, poison, and a Geiger counter. If the atom decays, the poison is released, and the cat dies. If not, the cat lives. Quantum theory suggests the cat is both alive and dead until observed. This paradox highlights the clash between quantum rules and everyday experience. The EPR paradox and entanglement. In 1935, Einstein, Podolsky, and Rosen, EPR, challenged quantum mechanics with a thought experiment suggesting it was incomplete. They described entangled particles, linked such that measuring one instantly affects the other, even at great distances. Einstein called this spooky action at a distance, but experiments later confirmed entanglement as a real and measurable phenomenon, defying classical ideas of locality and realism. Interpretations of quantum mechanics. Copenhagen interpretation. The most widely taught interpretation, developed by Bohr and Heisenberg, states that the wave function represents our knowledge of a system. It collapses upon measurement, and physical properties are undefined until observed. Many worlds interpretation. Proposed by Hugh Everett in 1957, this interpretation denies wave function collapse. Instead, all possible outcomes occur in branching, parallel universes. When we observe a quantum system, we enter a world consistent with one of the outcomes. Pilot wave theory, Bohmian mechanics. David Bohm revived an earlier idea by Louis de Broglie. Particles have definite positions guided by a pilot wave. This restores determinism, but at the cost of introducing non-local hidden variables. Objective collapse theories. These theories propose that wave function collapse is a real, spontaneous process triggered by certain conditions, not observation. Examples include the GRW, Ghirardi-Rimini-Weber model. Quantum technologies and applications. Quantum computing. Quantum computers use qubits, which can exist in superpositions of 0 and 1. This allows them to perform certain computations exponentially faster than classical computers. Algorithms like Shor's, for factoring, and Grover's, for searching, show their potential. Quantum cryptography. Quantum key distribution, QKD, like in the BB84 protocol, allows secure communication based on the principles of quantum mechanics. Any attempt to eavesdrop disturbs the system, alerting the users. Quantum teleportation. Quantum teleportation transfers the state of a particle to another, using entanglement and classical communication. While it doesn't move matter, it enables state transfer without direct interaction. Quantum sensors. Highly sensitive sensors based on quantum principles are revolutionizing navigation, medical imaging, and gravitational wave detection. Quantum field theory, QFT. From particles to fields. Traditional quantum mechanics treats particles like electrons and photons as fundamental. However, to describe phenomena at high energies and relativistic speeds, especially those encountered in particle physics, we require a more general framework, quantum field theory, QFT. In QFT, particles are not standalone entities. Instead, they are excitations of underlying fields that fill all of space. For instance, what we call an electron is a localized ripple in the electron field. Similarly, photons are excitations of the electromagnetic field. This approach merges quantum mechanics with special relativity and forms the foundation of modern particle physics. Quantum electrodynamics, QED. One of the most successful QFDs is quantum electrodynamics, QED, which describes the interaction between charged particles, like electrons, and light photons. Developed by Richard Feynman, Julian Schwinger, and Sunitaro Tominaga, QED provides predictions accurate to many decimal places. Feynman's diagrams became a revolutionary way to visualize and calculate interactions in QED, representing particles as lines and their interactions as vertices in a space-time graph. Quantum chromodynamics, QCD. The strong nuclear force, which binds quarks inside protons and neutrons, is described by quantum chromodynamics, QCD. In this theory, quarks carry a property called color charge, not related to visible color, and they exchange particles called gluons. QCD explains why quarks are never found alone, a phenomenon called confinement, and why protons and neutrons remain stable in atomic nuclei. The Standard Model. The combination of QED, QCD, and the electroweak theory, unifying electromagnetism and the weak force, forms the standard model of particle physics. This model successfully describes three of the four known fundamental forces: electromagnetic, weak, and strong interactions, along with all known elementary particles. The discovery of the Higgs boson in 2012 completed the model by confirming the mechanism that gives particles their mass. Quantum gravity and unification attempts. The problem of gravity. Despite its success, the standard model does not include gravity. While Einstein's general relativity describes gravity as the curvature of spacetime, it remains a classical theory. Attempts to unify gravity with quantum mechanics have proven extremely difficult. String theory. One prominent approach is string theory, which replaces point-like particles with one-dimensional strings. These strings vibrate at different frequencies, giving rise to various particles. String theory naturally includes gravity by predicting a particle called the graviton. It also requires additional dimensions, up to 10 or 11 total, to be mathematically consistent. Though elegant, string theory remains unproven, as it currently makes no testable predictions. Loop quantum gravity. Another approach is loop quantum gravity, LQG, which tries to quantize spacetime itself, suggesting that space is made up of tiny, discrete loops. Unlike string theory, LQG doesn't require extra dimensions, but it's also not yet complete. Both string theory and LQG represent ongoing efforts to develop a theory of everything, a unified framework for all forces and particles in nature. Philosophical and spiritual implications. Reality and observation. Quantum mechanics challenges our notions of reality. In the quantum world, observation isn't passive, it determines outcomes. Before measurement, particles exist in superpositions of all possible states. After measurement, the system collapses into a single state. This raises deep questions. Does reality exist independently of observation? What is the role of consciousness in quantum events? Some interpretations suggest that consciousness plays a role in collapsing the wave function, although this remains highly controversial and unproven. Free will and determinism. Classical physics is deterministic. Given initial conditions, future states are predictable. Quantum mechanics, by contrast, introduces fundamental uncertainty. This unpredictability is not due to ignorance, but to the nature of the universe itself. Some thinkers see this as room for free will, while others view quantum randomness as merely replacing determinism with chance. Quantum mysticism and misuse. Some have tried to link quantum mechanics with spirituality, mysticism, and consciousness. While it's true that quantum physics raises philosophical questions, many such claims stretch the science beyond its meaning. It's essential to distinguish between legitimate philosophical inquiry and pseudoscientific interpretations. Quantum mechanics does not prove telepathy, parallel lives, or energy healing, despite what some popular books or films may suggest. Future frontiers in quantum science. Quantum computing advances. Quantum computers are still in their early stages, but rapid progress is being made. Companies like IBM, Google, and startups like Rigetti and IonQ are competing to build powerful fault-tolerant quantum machines. Quantum computers could revolutionize fields like cryptography, breaking classical codes, or building unbreakable ones. Drug discovery, simulating complex molecules. Material science, designing superconductors or new batteries. Artificial intelligence, enhanced algorithms using quantum logic. Quantum internet. The quantum internet is an emerging technology that would allow entanglement-based communication over large distances. It promises unhackable data transfer, based on the laws of physics rather than computational difficulty. Researchers are already building small-scale quantum networks, and China's Michia satellite has demonstrated long-distance quantum communication from space. Quantum metrology. Quantum effects are also improving measurement technology. Atomic clocks using quantum transitions are the most precise timekeepers. Gravitational wave detectors like LIGO use quantum techniques to measure tiny distortions in space-time. Quantum sensors can detect magnetic and electric fields at unprecedented levels, beyond the standard model. Physicists are searching for new physics beyond the standard model. Supersymmetry, a proposed symmetry that could explain dark matter. Axions, hypothetical particles that could solve the strong CP problem. Neutrino oscillations, hint at unknown physics like sterile neutrinos. Dark energy and dark matter. Quantum fields might explain these mysteries. The quest continues to uncover the ultimate laws that govern the universe. Conclusion: embracing the quantum world. The quantum world is strange, counterintuitive, and deeply mysterious. Yet, it is also one of the most rigorously tested and successful scientific theories ever developed. From atoms to transistors, lasers to MRI machines, and quantum computers to philosophical debates, quantum mechanics touches nearly every aspect of modern life and thought. It teaches us that reality is not what it seems, that particles can be waves, events can be uncertain, and distant objects can be instantly connected. The universe is not a fixed machine, but a dynamic, probabilistic tapestry woven from possibilities. As we continue to explore the quantum world, we're not only uncovering the secrets of the cosmos, we are also redefining what it means to know, observe, and exist. If you have any experiences related to this topic, be sure to share them with us. Until the next episode, be mindful of the energies around you.